Okay, let's get started. I welcome you to the series of tutorials in computational chemistry. In this tutorial, we're going to see how to use the Gauss View software. The Gauss View software is the graphical interface for Gaussian. The Gaussian is the software in which the calculations are actually run. I believe you have installed the Gauss View on your computer. Once you have installed it and open it up, it looks like this. It has these three windows. We normally do not bother about this one. We close it as such. And now we are left with two windows. This window is the window with all the tools available inside it. And this is the tool for drawing of the structures. This is also called like molecule group here. Now in this tool window, you can see a number of icons here and a menu bar here. Now in the menu bar, there are many options available, and most of those options are also available here through these icons. We're not going to see all of these icons in this tutorial, or all of the functions of Gauss View in this tutorial. We will start from the very basic, that how to draw a structure in Gauss View. So before I start how to draw this structure, just want to let you know that these are the two icons that are for the creating a new molecule group or adding to a molecule group. For example, if I close this window and if I click this one here, I can get that window. I can do the same thing by clicking on File and New Molecule Group, and you can see the shortcut is Control plus N. And you can see the plus sign is also available here. So in this menu bar, you will see symbols here. These icons are also available here. For example, this is for opening, saving, print. So those options are available here: opening, saving, print, and so on. Similarly, you can go to edit, you can find these different options, and on the side you will see different icons here, and those icons are available in this icon menu here. Anyways, now we go to this drawing of the structure. When you open up this Gauss view, by default it says carbon tetrahedral here, and the structure that is shown here is of carbon tetrahedral. The very first example that we are going to draw here is of, let's say, the simplest molecule like a hydrocarbon chain, maybe pentane or hexane. If you want to do that, you just simply need tetrahedral carbons, because if you're drawing pentane or hexane, all of the carbons are tetrahedral. But if you click on this carbon tetrahedral icon here, you will see the entire periodic table. And in this periodic table, you will see all the elements as well as they're all different bonding modes. For example, if you talk about carbon, you can have carbon tetrahedral, you can have carbon trivalent, but that trivalent is more like of an aromatic system. This is also carbon trivalent, but that is more like an alkene or carbonyl. This one is divalent of allene, divalent of alkyne, and this is simply a carbon atom. Similarly, for any other element in the periodic table, if you click, let's say if I click on nickel, I can see the option of nickel atom, divalent nickel with 2 bonds and a linear structure. Now, nickel with 3 bonds, trigonal planar, 3 bonds T-shape, 4 bonds tetrahedral, 4 bonds square planar, 4 bonds seesaw, then 5 bonds like trigonal bipyramidal, 6-bond octahedral, and some higher structures and different symmetries. Anyways, we come back to our drawing of carbon with tetrahedral. Now, if I close this window, now this is carbon selected here. I just need to click in this window, and you can see I have placed the molecule of methane. Now, if you select or if you click on the hydrogen here, this hydrogen will be replaced by a carbon. If you click on this hydrogen, it will be replaced by carbon, or you can click on this one or this one. Let's we do this, and we do this, and that's it. Now you can see here we have drawn the structure of an hexane. One thing that I want to tell you here that you need to pay attention to, now in this structure here, the central carbon atom is shown by bluish green color. But if you click on this hydrogen here, now you can see this hydrogen is now getting the bluish green color. Now this color indicates that which atom will be used for bonding. Previously, when carbon was selected, I was clicking on hydrogen and that hydrogen was replaced by this carbon here. But now if you select this hydrogen here and you click on this structure, you will see a difference here. Instead of replacing this hydrogen with a carbon, you can see it added in a different way. It made bonding through hydrogen because the hydrogen was selected here. If I do Control Z, I go back, and if I select this carbon here, I can click on this one and you will see bonding through carbon. So this is just the point of caution that you need to make sure that you are clicking the right atom in this window, and that will be connecting through that carbon in this molecule here. Anyways, the target was to draw the structure of hexane, and that's it. We have done this. Now, we go to the next example. Okay, now we move to the next example. At this point, we'll take the help of the second icon here, which is for the ring fragments. And now you can see here, if you click on this ring, by default, it shows benzene molecule. And if you click on this benzene here, you will see a list of different ring fragments available, like benzene, biphenyl, naphthalene, anthracene, phenanthrene, and so on. And some of these ring fragments are even more complicated, like bicyclic, cis-decalene, trans-decalene, we can have C6T, we can have adamantane. But let's say we are interested in drawing the structure of this compound, binaphthyl type compound with 2 alkyl groups here. Now, for drawing this molecule, we need to have 2 naphthalene units connected with one another. And let's say we select naphthalene fragment from here, put it in this window, just click it here. And we want to make a bond. Let's say we click again here, and now what we get is binaphthyl fragment. At this point, I just want to bring one thing in your attention, that if you look into this structure here, it does not show single and double bonds or partial double bond. Although when you selected the naphthalene fragment here, it was showing partial double bond, just like aromatic system here, but you're not seeing those partial double bonds here. It depends on the style that you have chosen, but even if it is not showing the double bond, it does not make any difference, because in computational chemistry, the software is actually looking at the separation between atoms rather than the bonds that you draw by yourself. In molecular mechanics, a type of calculation, we generally care about the single and double bonds that we give to the software because molecular mechanics takes into account the single and double bond and then calculates energy. But for quantum mechanical methods like Hartree-Fock, DFT, semi-empirical, or post-Hartree-Fock methods, they all depend on the spatial coordinates and they do not depend on the bonds that you have shown in the structure. Now, if it is even showing a single bond here, as long as this distance is appropriate for aromatic system, the system will or the software will consider it as the right structure. Just to make sure that the bond lengths are appropriate, you click on this icon which is for bond length. If I click this one and select any two carbon, and we know that if it is carbon-carbon single bond, the bond length should be around 1.54. If it is purely carbon-carbon double bond, the bond length should be around 1.34. And if it is aromatic type system, then this bond length should be close to 1.43. And if you look at the value here, it is showing 1.422, which is more close to the aromatic type bond. And even if you see here, the bond type is aromatic type, although it's not showing a partial double bond here in the structure. But if you look into the properties here, it is showing a partial double bond, just like aromatic system, or 1.5 bond. Anyways, now we have made sure that the structure is drawn correctly. Now we need to install the ethyl groups. We have seen we have two ethyl groups here. And now we are going to put the ethyl groups. To put ethyl groups, we need to select this carbon fragment. Again, select carbon tetrahedral. And I click this one, and now you have one ethyl group placed here. You can do this, and you can have the second ethyl group placed here. Now, in this structure, I have intentionally chosen this structure just to reflect one thing. Now, if you see or you pay attention to this molecule, these two atoms, they have come very close in space. Similarly, these two hydrogens have come very close in the space. And as I just mentioned that the software looks at the atoms through their Cartesian coordinates. So if any two atoms are close enough for being considered as bonded by the software, although even we do not have bond between them, the software will try to think as these two atoms are bonded together, and it will try to make bond here or adjust the bond here, and that will ultimately destroy the structure. So to overcome this problem, we need to increase this separation and increase this separation. And one easy way to increase this separation is to change this dihedral angle, the angle of one naphthalene ring with the other naphthalene ring. How can we do this? We can do this by selecting the appropriate dihedral angle. So close to this bond length icon, you have bond angle icon, and then we have dihedral angle. Now, if I select this dihedral angle icon, and now I can select an appropriate dihedral angle, since I'm going to rotate one naphthalene with respect to the other naphthalene ring, so the bond between two naphthalene rings should be midpoint of this dihedral angle. In dihedral angle, we select 4 atoms. So the second and third atom should be the bond connecting to naphthalene ring. So if I select this one, you can see I have selected 1, 2, 3, and 4. The second one and the third one, they are connecting to naphthalene ring. So it means I have selected the appropriate dihedral angle. And you can see currently this angle is about minus 56 degrees. And if I set it to like, let's say minus 90, that will make these two naphthalene rings perpendicular to one another. And now you can see, once I have made these two perpendicular, those two hydrogen atoms are no longer close in the space. So you can see the distance between this hydrogen and this one is increased. Similarly, the distance between this hydrogen and this one is also increased. Now, let's say after having drawn this structure, we want to put like OH group on these ortho positions. We can put one OH group here, one OH group on this carbon. And we are going to make a like binephthol type structure, which is a good ligand in catalysis. To put OH group, I go back to this periodic table, select oxygen. Since I have to put OH group, this carbonyl type oxygen is not the appropriate one. This type of oxygen is more appropriate. If I select that one, click here, I get OH group. If I click on this hydrogen, I get OH group. So I have placed two OH groups. So with this one, our second part of this drawing is over. We have seen how to use elements from the periodic table, how to use a ring fragment. And in the next example, I will show you how to draw a metal complex. Let's say we talk about now a metal complex. We can select a new window, Control N. And let's say we're interested in drawing the cobalt complex with 6 water molecules. So for 6 ligands around cobalt, the structure is octahedral. So I need to select cobalt octahedral from all these options available. And if I click here, what I get, cobalt with 6 hydrogen, because the default in Gauss view is to have hydrogen around the atom of your interest. So I have the element of interest as cobalt, and I have these 6 hydrogen. But I need to put 6 water molecules. To put water molecule, I need to select oxygen and with 2 bonds here. Now you will see that the computational software will behave slightly odd here, not as you were expecting. Once you click on this one, it puts OH group rather than a water molecule. Although it is showing a water molecule here, OH, but as soon as you click here, it does not put water molecule, it puts OH group, because the software is assuming that you have made a covalent bond here rather than coordinate covalent bond here. So if it is a covalent bond, then the bond between oxygen and cobalt should be considered as a covalent, one bond here and the other bond to this OH. You can do this to all the atoms, and now you have 6 OH group, but not the 6 water molecules that you were trying to put there. So we have to convert this OH group into a water molecule. How can we do that? If we can add one extra hydrogen here on each oxygen atom, this OH will be converted into a water molecule. How can we do that? It's quite simple. You can see this icon here, add valency. You can see this hydrogen sign. If you click on this hydrogen symbol, now you can add valency here. If I click on this oxygen, I have valency added. Now it becomes water molecule from OH. You can do this here, and this one. I'm not sure whether you have noticed or not. When I was adding the valency here on each oxygen atom, the angle was slightly changing for OH. But anyways, now we have the structure with 6 water molecules around cobalt metal center. And now all of these bonds can be treated as coordinate covalent bond. Up till this point, we have seen how to draw the structure. We did not save any input file, or we did not go for running a calculation. We have one more thing to do in this drawing before we can go for submitting a job, or we can save the file. Let's say we go to the next part where we can we go to the next part and we can see here a number of different functional groups are available here. If I click on this icon with R here, it shows me R group fragments. How many groups are installed herein? You can see if you click on formal, it's like ethane or like ethyl group here, N-propyl, isopropyl, N-butyl, tertiary butyl, vinyl, ethynyl, like aldehyde or ketone. Then I have carboxylic acid and so on. You can see here it keeps on going to like maybe 3-membering, 4-membering, CP9, tropylium cation, and so on. So if you want to put these groups here on any structure, let's say if I take the example of benzene, I put benzene here, and now let's say I want to add some functional group here, maybe nitro group. I can select this one here. I need to make sure that I'm going to make bond through nitrogen atom, not the oxygen atom. This one should be greenish or bluish green. I click here, I put nitro group here. And the next icon here is the biomolecules. If you select this icon here, it gives you option for biological fragments. And in biological fragments, you have 3 different types: amino acids, nucleoside, or others. If you select amino acid, you can have all different amino acids listed here, like alanine, arginine, asparagine, and going up to valine. All these amino acids are listed here. Not only the amino acids are listed here, but also their bonding style is also given. You can select alanine as a central fragment, amino terminal fragment, or carboxyl terminal fragment. Let's say we draw alanine first as a central fragment. Once you draw it as a central fragment, you can see that its carboxyl terminal is also empty for further bonding. This N terminus is also empty for further bonding. Now, if you select alanine as amino terminal fragment, I can put it here and you can see I have now amino terminated fragment here. If I put alanine as carboxyl terminal fragment, I can click on this one and I can generate carboxyl terminal fragment. The other option is you can select nucleoside. The same options here. You can have a number of different nucleoside: deoxy, adenosine, deoxycytidine, and so on. Similarly, you can have option to place it as a central fragment, C terminal fragment, C5 terminal fragment, or free nucleoside. Or the third option that you can see is other. In this others category, you will see 2 fragments there, like ACE for acetyl and NME for N-methyl amine group. And the last icon here in this drawing tool is clipboard. When you're working in Gauss view and you want to copy one structure from one window to the other one, you select it and it goes to clipboard. When I was using previously Gauss view, I selected a 3 amino acid chain, and probably that should have been copied to clipboard. Now, if I click that one, I can see what was copied in the clipboard when I was using Gauss view previously. And now you can see here, it's a 3 amino acid fragment here, and that was copied to clipboard. And even if I click on this clipboard here, I can see only one structure because it is the only structure that you copied previously, and that is stored in the clipboard. So anyways, now we are done with simple drawing. We have seen carbon, like all periodic table. And in the periodic table, we have seen different bonding modes for each element. One thing which I missed out, you can see in this periodic table, two elements are extra. One is called as like X and the other one is called BQ. X is for dummy atom and BQ is for the ghost atom. We generally do not use these elements unless we specifically need to use them. Probably I can give you an example of NMR when it comes to Nix calculation, where this ghost atom or dummy atom is used. Then we have seen ring fragments. We have seen all different kinds of ring here. Then we have functional group, these biological fragments, and now we are done with the drawing part.